did it. The first camera you did it. Search it. Louis Lane.
Did you get my email that, after fall break, I'm not here on October 12th? Did you get the message I sent on Blackboard?
Maybe I didn't check.
I didn't see it.
Did you get the homework?
No.
You didn't get the homework?
We were surprised.
Yeah.
We
We
checked.
were talking about it.
We were
Yeah,
talking
we didn't get
about it.
homework.
You didn't? Yeah, I sent it on that day, but last class. Yeah, I did send a homework too.
Maybe it's in the week by week. Did you check?
Assign.
Week three or-
Did you post it in
I
class
thought
open?
I thought I even put it at 2 different locations.
No, we have items.
I even posted a message announcement.
Announcement. There is no announcement. That's for sure.
No announcement.
Yeah, I didn't see one either.
Yeah.
Okay, that's interesting.
Where else did you post it other than announcements?
Huh?
So it'd be under assignments only has homework 3 and 4.
This was, I had given 3 problems. I mean, that was on, what was, today's Tuesday, right? Thursday I posted one, yeah.
No, just
I'm just wondering where it went then.
Maybe it's in week.
I mean, not only that, I even put an announcement too.
Content. Let's open the course content and schedule.
Let me just see where I put it. Let's go to,
Course content.
this is mine,
And now week 5.
assignments. No, I didn't put it there at all. I think I put it in assignments.
But
Nope.
maybe it's
Where did it go? Announcement also didn't come, that's a
Yeah.
bit strange. Because that is
The
a,
latest one is the test one.
yeah, so you didn't even get the announcement because that's a separate location, right? I mean, it's not even in the assignment location, so
just check for the course
Uh,
content.
let me just,
And then
Week
you think
5.
it's on the
Week
bottom?
5 because
That's where homework 2 was.
week 5.
I didn't put in week 5 and all,
Week 4.
Maybe week 1.
I don't even get, I mean, I don't see, what I see is slightly different. So announcement, because I spoke with her and I said I'm going to post everything. So anyway, first I'll repost there are 3. One was derivative method, what was it? And then one was on
Integral.
integral representation. And there was one more problem. What did we do now?
Bessel, I think.
I know, it was one, I gave 3 problems actually. Let me just, it was homework 5, so I will repost it, okay? I was a bit surprised, okay. Anyway, the main thing that I want to tell you is I'm not here the week after fall break. The fall break is covering Tuesday, right? So we don't have a class on Tuesday, but you will not have a class on October 12th, which is, I think, it's a Thursday. Yeah. So I'm also thinking, because October 19th is your test number 2, am I right? So I'm thinking of postponing that to, Tuesday. Or, yeah, I mean, because I want to cover Green's function method in homogeneous differential equations.
The test was going to be the week after the fall break week?
Or it was on October 19th, if I remember correctly.
So you want to put it 2 days later?
Yeah, I mean, yeah, after the weekend, I think, yeah. I was just thinking, 24th, I thought I'll do it. Is it 24th? Is it Tuesday?
That sounds right.
Yeah, right. So 24th is what I want to, I mean, that will be comfortable now that the homework is also not being done, right? I mean, I was wondering why nobody asked me questions about it. One was derivative method, one was that, and was one more problem. I don't even remember what it was. I gave 3 problems. Oh, one was on the hypergeometric functions to identify some transformation. Yeah. So those are the 3 problems I've given. Yeah. So I will repost it if it send via email to all of you guys. I mean, maybe that way. It didn't complain, nothing. I mean, it didn't say anything that it didn't. I even thought I posted homework at 2 different locations. I somehow felt. Anyway, I'll check what's happening. Yeah. All right. So what I want to do today is get started with this other one, confluent. Okay. It's given by this particular formula. So last time what we studied was the hypergeometric differential equation, which was given by the following. I'm just wondering whether I posted in incorrect year. Who knows?
Yeah, maybe.
But still, but that should be closed. I mean, yeah, that's the only thing I can think of. Because I have other years, the previous year.
Yeah.
But that should be closed for me. Anyway, we'll see what
You
happens.
can edit stuff and not submit it.
I thought I was in the assignment section. Anyway, we'll check. I'll check. Yeah, very good. This announcement and all, it should not let me go back in a previous year or something. Alright, so this is hypergeometric differential equations, and we saw that for proper choice of A, B, and C, we could get Legendre differential equation. That's what we had studied last time. At least we covered that. So here, if you look at it, it has, x equal to 0 is definitely a singularity, and as I said, x equal to infinity. This will have 2 singularities, x equal to 0 and x equal to infinity. I'll prove to you for Legendre differential equation today, a little bit later, so that we understand that particular concept. So what, and we saw for this particular case, the solution is given by, at least one of them is given by a, b, c, x, the hypergeometric function, right? And this hypergeometric function was nothing but 1 plus ab over c times x. This is what we got last time. B times b plus 1, c times c plus 1, x squared over 2 factorial. This is the infinite series, and this infinite series could become a function in certain cases. This is what we had done last time. So what I'm going to do is, I know this differential equation we solved exactly by the power series method, that, right? I mean, I'm going to say that if I, from this differential, knowing this and the solution of this, that is one of the solutions, the other one was x power 1 minus c times, a became, c became 2 minus c, and a became what, a plus 1 minus c, b, right? I mean, all that we transformed. So what I'm going to say is, I'm going to go from here to here, this differential equation, by some transformation. And wherever x occurs, I'm going to replace this, make this substitution. Okay, and then I'm going to let b go to infinity. So this, we said, has 3 singularities. Okay, x equal to 0, x equal to 1, and x equal to infinity. And by making this transformation, it will collapse to 2 singularities, especially when I make b tend to infinity. And I I'm not going to solve it explicitly. I'll just get the solution from f to another function, which is a confluent hypergeometric function, or also called Kummer function. Okay, so that's what we are going to do. We're going to start from here, and then say that if I make this transformation x equal to z over b, and let b go to infinity, then the hypergeometric differential equation becomes and you can get the solution accordingly, okay, because we know already the solution of that, so we'll try to get it. Okay, that's what I'm going to do for you right now. So let me write down these things. All right, so this is what we are trying to do with b tending to infinity on this particular equation, confluent hypergeometric differential equation. All right. So if if this is a transformation, I do have what dx is 1 over b dz. That's what I have, and all I have is what y prime is a function of x here. I want to transform this to another function, let us say yx. I want to transform that to another function u, which is a function of z. Okay, by making that substitution. So y prime of x is dy over dx. I want to convert that into what? Du over dz. Dz over dx, because I'm changing yx to this. So dz over dx is nothing but b. So this is nothing but b times, this becomes y prime of x maps to b times u prime z. Okay, so this becomes that, right? Similarly, y double prime of x in our case will become b square u double prime z, right? You can just do it again, right? I mean, so y double prime x is nothing but dx over y prime, and this is nothing but d over dz, dz over dx, and this is already y prime mapped to that, right? That mapped to that. And I get dz over dx, I get under this thing. So this will become b square u double prime z. The same kind of mapping. Okay, so that will become that. And then we just substitute everything here, and then let b equal to go to infinity to check what's happening. X is z over b. 1 minus z over b, and y double prime is b square u double prime function of z, right? Plus c minus a plus b plus 1, x is z over b, y prime is south side, right? B times u prime z minus aby, or u of z now, equal to 0. All right. So this I can write as z, b minus z, b square will cancel, so I can write it like that. All right, plus, let me just for a minute write down like this, minus a plus b plus 1 times z a b u z equal to 0. Okay, this is or bz, a plus b1 z, and the b will cancel. U prime of z minus ab u of z equal to 0. Right? And I want to examine this equation in the limit b tending to infinity. So what I'm going to do is pull b out. So I'm going to call this as bz 1 minus z over b. Okay. B will get cancelled. Okay. So if I want to pull b out, I have c minus. In this term, it's a over b plus 1 plus 1 over b times z, okay, times u prime of z minus a b u equal to 0. All right, b is common everywhere. That I can, take out, factorize out. Okay, b is common everywhere, here and here. Okay, so if I factorize that out and then let b tend to infinity, this term will be 0, this term will be 0, and this term will be 0. So I end up with the following: z times u double prime z plus c minus z, okay, times u prime z, the first derivative of u, minus a times u of z equal to 0. Okay, so which is my first equation, right? Here the variable, independent variable is x. Okay, instead of that I have z u prime double prime c, c minus z, first derivative of u minus a u z, which is nothing but confluent hypergeometry equation. Is this clear? We factorize this and then let b tend to, take it out and then let b tend to infinity. Then what I've done is transformed your hypergeometric differential equation to confluent hypergeometric. All right, is this clear? All right, and this one had solutions. One of the solution was f a b comma c x, and the second solution was x to the power 1 minus c f of, if I remember, it is a plus 1 minus c. That this I think is b plus 1 minus c, and this was 2 minus c x. Okay. So those are the two solutions. And now I'm going to apply this, right? We know what, wherever x was, it has to be that. And I have to let b tending to infinity. These are the two things I will apply to the hypergeometric differential, hypergeometric function to get the confluent hypergeometric function. Okay, so that's what I'm going to do. Is this clear up to this? Whatever transformation I've done, all I've done is x as z over b in this, and I made b go to infinity, and that transforms this equation to that equation. And since I already know the solution of this, which we have done by the power series method, I'm going to apply this to that and get the solution, the first solution of the confluent hypergeometric differential equation from there, rather than explicitly solving. Of course, you can solve this explicitly using power series method or Frobenius series method. Okay, so that's what we're doing. We're going to do. All right. So if I do all those things, what do I get? 1 plus, at this point I'm going to write it a b over c. X is z over b, plus a times a plus 1, b times b plus 1. X square is z square over b square, and then I have 2 factorial. Okay, all that stuff. So all I've done is replaced x by that. Okay, here at least I can see b and b are cancelling. That's not a problem. But here I will do the same trick as we did previously. I'm going to take b out. If I took that b out, this is nothing but b square 1 plus 1 over b, right? So, and in the limit b tending to infinity, what will happen is this will become 0, and this b square will cancel with this b square, and I will end up with the following series: a over plus a times a plus 1 divided by c, or c plus 1. Okay. So this is nothing but that b square cancel. All I have is z square over 2 factorial. So you can now understand how this series is going to be: a plus 1, a plus 2, c plus 1, c plus 2, z cubed 3 factorial, and so on and so forth, right? I mean, and this function, this series that you get, if it converges into function, is called as Kummer function, or based in the name of the person who wrote it, and or confluent hypergeometric function. And it's function of only 2 variables, a and z, and this case, of course, because variable is z, so this has become this, or confluent hypergeometric function. All right. So this equation, I mean, the second solution also I'm not, I mean, if you do it, get the roots, initial roots, you will get one of them as before, you'll get one of the roots as 0. The other root, you'll get it as 1 minus c in this case also, okay? So the second solution is also written, you know, you can write it by guessing basically here. Frobenius series, you have x of sigma, so you have x of 1 minus c, and m a minus c plus 1, there are only 2 of them here, 2 minus c x. So this will be the form of the other solution, and you can replace wherever a occurs, you have to replace by a minus c plus 1, okay, and c you have to replace by 2 minus c. Yeah. So you have to replace a by that, and 2 by c by 2 minus c in this expression. So this one will be nothing but a minus c plus 1, and the denominator will be 2 minus c. Okay, so as we did previously. Okay, so that will be your solution, this infinite series. That is it. That's what this notation means. Okay, may not. So these will be the two solutions. Y1 x will be this one, m a c x. If the variable is x, just put it, or z, you just put it as z. Okay, so that is your independent variable. So what is this quantity m a z?
This is for, I think it's a series. 1 plus z plus z square. Z plus z square by 2. Is e to the power.
It cancels, right? So it's exponential of z. Okay, so what I'm trying to say is this, depending on the variable, it could corresponding to some known functions. And advantage of this is, of course, for our purposes, advantages is whether it corresponds to any of the special functions, right? I mean, rather than write it in terms of Laguerre or Hermite, you can write it in terms of this Comer function, and you will see in the books, in that form. So Laguerre is, for instance, Laguerre differential equation is given by the following. Of course, you can always solve by the Frobenius method, but the solution of this, the Laguerre polynomial, that is, a series becomes a polynomial, then in that case, it's given by the following. A you have to replace by negative n, whatever here. I think the other one is 1 and x. Okay. So this is A, and this is your value of c, and the independent variable is x. We are not making any further transformation of this independent variable. So that will give you Laguerre polynomial. But I mean, this is a different notation, so I just want you to be aware, that's all. I mean, quantum mechanics books will write it in terms of this. I mean, just as we saw Legendre polynomial was written in terms of f, right? I mean, but there it was, this variable I have to change to 1 minus z over 2 or something like that. So they will interchangeably, use this notation or that notation, so that way you need to understand both notations. Okay? So this is, we didn't go over this, but we'll do it in quantum mechanics. So this is a polynomial, Laguerre polynomial. Just as you have Legendre polynomial, it's on the series which gets terminated and all that for terminated if this is a integer. Okay, so no general way of writing this is new, but if this is an integer, that series, whatever R series solution you will get terminated, and then you can represent by this also. Okay, so just I want you to be aware of all these complementary notations that you may come across. And similarly, Hermite can also be represented. I just wanted to show you for exponential because that's at least I mean, you can see that. So this is sort of the advantage of that. Hermite is given by the following: minus m. These are only, I think, most useful ones. The transformation independent variable goes to z square here rather than z, and then it produces the Hermite polynomials, which come in your quantum mechanical oscillator. And I think you did the problem. I think it was a homework problem I had given you. You have solved for Hn x before, okay? So you can try to play with that. At least you did this. We did not. And I didn't give a homework problem on that, but you know how to solve it because everything is there. I mean, although it's called Laguerre or whatever it is, you don't even worry because it has x equal to 0. It has you use a Frobenius series and then you get the solution but you will get a solution in terms of infinite series. But if you don't even want to do that, you just have to put a equal to minus n. Where is it? You don't have this, right? I mean, b is not there for m. All you have to put is m, a equal to that. You have the solution already, right? I mean, you don't have that, so you know what it is. Okay, so that's what I'm trying to say. This is useful in that sense because these series are so easy to remember. I mean, they have a very nice structure. So without even doing anything, you already know what the Laguerre should be. Just all you have to do is have the correct values and you have the solution. Okay, so that is the key advantage of the whole method. You have to just open here. If you have to do that, look at how is it represented in terms of confluent hypergeometry function, and then you know this infinite series, and so that's all it is. Okay, so basically, I think what mathematicians have done is classified differential equation into two types, right? I mean, depending on some of them will fall under hypergeometric differential equation, and some will fall under confluent hypergeometric differential equations, and you can write the solutions very easily as long as you knew what the values of a and c are and all that. That's it. Okay, I mean, yeah. So any questions here? This is just I want to complete this because you will see this notation, and I want you to be comfortable with that. I mean, it's nothing, but everything is coming from, you have to know it's Frobenius series or ordinary power series that we have already done. But these are other ways of getting the solutions. That's it. All right. That's your Lejeune differential equation. So So this one, of course, when you look at it this way, we know is equal to plus 1 and is equal to minus 1. It has singularity, right? I mean, that we see it. So if you made this transformation, okay, then we do have what? dw is negative 1 over z squared dz, or dw over dz is negative omega square.
What we are doing? Means, what we are doing?
Yeah, what we're trying to do is, I want to show, remember I always said, Legendre, if you look at it, we don't understand why z equal to infinity is a singularity.
Yeah.
Because we classified this under three singularities, right? I mean, under hypergeometry differential equation. And I said last time, I'll show you why, there's a singularity at infinity also. I want to show you at least once why we are saying that. Why z equal to infinity is also singularity. Okay, that's what I'm trying to prove. So I'm going to say at omega equal to 0, you have a singularity
It's
for this.
related to green function.
Huh?
It's related to green function.
No. Green's function, we are going to do it for inhomogeneous differential equation. That we'll do later. All I'm trying to prove is
Okay.
why this Legendre differential equation has three singularities, right? And we classified that under hypergeometric differential equation. And I want to show that if I make this transformation, omega equal to 0 is a singularity. This is only for convincing you, otherwise it's not obvious, right? I mean, so I want to make this transformation and show you that at least once for one differential equation, so that way you understand why mathematician classified into two types. Okay. All right. So we have, this in this kind of thing, it's the same thing, right? I mean, so y of z, we are going to goes to something. The independent variable is w rather than z. Okay. So I can write this as okay. So this is getting mapped to that, and what is that? dw or dz is minus 1 over dz. Okay, dw is minus 1 over yeah. Okay, so this is nothing but and I can write this as negative omega square dz. So dw or dz is nothing but y prime becomes what? Negative omega square y tilde omega y prime of this mapped function. Okay, so this is what this has become. And what about d square y? D square y over dz square okay. And I want to write this as d over d omega, and this we have to, and this is d omega dz, right? And this one in terms of dy, when it becomes that, is negative omega square of y wiggle prime omega. Okay, so this is what we got, dy dz, and this side that gets mapped into negative omega square y tilde of prime omega. Okay, and this we can again d omega or dz, I can write it as negative omega square d over d omega of minus omega square y tilde prime omega. Okay, so this is what d square over dz square becomes in this case. And so he's got two terms here in this case. D square over dz square has become negative omega square of, let's put this is minus 2 omega of y tilde prime omega minus omega square of y tilde double prime as a second derivative with respect to omega. Let's see. This one is minus d omega over dz is negative omega square. I got that. Okay. Okay, and this is minus 2 omega, that, and that. Okay, all right. I got all that term, I think, all right. So this is nothing but, let me just maybe write it as 2 omega cubed of y prime omega plus omega of 4 y double prime omega. All right. All right. All right. So I can write z is 1 over omega. So I have 1 minus 1 over omega square, right? Z is that. And y double prime has now become all that stuff. It's a little bit more complicated. That's okay. Omega to the 4. Okay, that plus 2 omega cube y prime of omega, okay, minus 2z. Z is 1 over omega. Y prime is here, negative omega square y wiggle prime omega plus L times L plus 1 y tilde omega. Okay, here anything. So that transformed to that, I think. All right. All right. So I just have to, I've transformed this original equation in independent variable z to something in omega. That's what we have done. So let's start collecting the terms. So the first term here, all right, so I have something which is y double coefficient of, that will, the coefficient of the first term would be what?
Omega 4.
Omega 4 minus omega square at this point, which I can write as omega square minus 1, right? I mean, it looks like.
Yeah.
Can I write it like that? Okay, that will be the first term. And then y wiggle prime omega, that's the first derivative term, has got some of them. Let's maybe something cancel, I don't know. Let's see. So what I have is 2 omega cubed is one of them, right? Minus 2 omega y prime. Okay, so 2 omega cubed y prime right? Minus 2 omega, because that will cancel. And I think this becomes plus 2 omega, so that will cancel, it looks like, right? I mean, this is a minus 2 omega y prime, okay, omega. So I think I'll be left with this only when I combine them. Just check it.
2 omega cube plus omega.
That's it, right? And then I have that, which is our L times L plus 1 y tilde omega equal to 0. So my original Legendre differential equation has become this. So what is my P, let me call this P omega. What is that? And for this differential equation, what is P?
P omega is omega into omega square minus 1.
So 2 omega cubed, right? Divided by omega square minus 1. Q omega, on the other hand, is L times L plus 1 divided by omega square times omega square minus 1. Okay? So what is happening at omega equal to 0? Which is the, why is it now a singularity? So I have this, which is a coefficient. I have to make, for getting the coefficient of P, I have to make that coefficient 1, right? So I have to divide through by omega square minus 1. So my P omega is okay at omega equal to 0, it is 0. It is Q omega which becomes 0, okay? So Q tilde omega at omega equal to 0 is infinity, and making omega equal to 0 as a singularity, and hence z equal to infinity is a singularity. So it's a, yeah, so what we proved is when you transfer omega equal to 0.
But this also gives that plus minus 1 also.
Yeah, of course, 3 singularities. I need to have 3 singularities.
This transformation exactly gives 3 singularities.
Yes, yeah. That is what we are trying to, because remember this Legendre differential equation, I could get it from Legendre polynomial, I could get it from hypergeometric function f.
Yeah.
So we are just checking, whatever they say, 3 singularities will fall under that category, and so and it is not obvious when you look at this form, the way we have been looking at it, right? Because we were mostly interested in Frobenius series around which point we want to make the expansion, z minus z naught, right? We wanted to do it. In fact, when we did the problem, if you remember, we didn't even expand around z plus 1 or minus 1. We did it as an ordinary point, because z in Legendre, most of them is cosine theta between minus 1 and plus 1. I was using ordinary power series to get the Legendre polynomial series. If you remember, we didn't even go through the Frobenius series method. Okay, so I just want to, so it's not obvious from here. And why did they classify under hypergeometric differential equation? And it is only how to count the number of singularities. It's not where it is located they're worried about. It's the number of singularities they're worried about. Okay, so even when you make like the other day we were talking about arbitrary transformation. The number of singularities is not good. It may change from, if you've made a very funny transformation.
This is the more, you can say, more convenient differential equation for Legendre.
I'm not saying it's convenient, but why is this classified under hypergeometric differential equation? The analogy between, that's all we are trying. It's
That's
not.
We get, but
Yeah.
We didn't use this differential equation to solve.
No, we did not. Yeah.
Because
This is only to
it
convince.
is more complicated.
It's more complicated, yeah. In fact, yeah. We are not doing that. We are just only trying to convince ourselves why, z equal to, there's one singularity at infinity also. I mean, which is not obvious. By looking at it, we'll say z equal to plus 1 and minus 1 are the only singularities, right? Because we are more interested in Frobenius series is possible or not, okay? For which that guy Fuchs said, you must have z times p of z should be, finite, and z squared times q of z should be finite to have that expansion. But this is, just to see the number of singularities itself for a given differential equation. That's how the classification they have given.
We can say that it's more general differential equation.
Yes, that's what. Yeah, it's a more general. They're trying to unify and see.
Yeah.
rather than how many every time solving this by
Usually for solving purpose, we usually make transformation. That's what we do.
no more than that. If you did not know about this,
Yeah.
what you will just automatically say, let me analyze P of Z and Q of Z, and then you'll go through the Frobenius series or power series ordinary power series method to get the solution, which is a lot of steps.
Yeah.
Now if you know they are going to fall under this category, that
This
category,
then
it is sort of a little bit more straightforward to get the solution in a more easier way. That's all it is. I mean, because you're not going to every time go all the way, keep on doing for different types of differential equation. So all that is doing is somebody decided to classify, and can we find some general structure in some of these second order differential equations. That is the advantage. That's all it is. And I just want you to look at it at least once, so that you're not making it up. I mean, there's one why it is. You have to do that, some kind of transformation like that, to understand z equal to infinity or x equal to infinity also. So the transformation will be just on the variable, which is just inverse of that, and try to see for z equal to omega equal to 0, if it becomes, that means z equal to infinity is a singularity. Okay. That's all. All right, I'm just trying to tie up some loose ends, right, before we go to other topics like inhomogeneous differential equation, other topics. So the other thing which I want to touch upon today is spherical Bessel differential equation. And if you remember when we solved the Helmholtz equation, this partial differential equation in spherical coordinates, one of the differential equation R was transformed into something of this nature, became a spherical Bessel differential equation. Okay, so this is called a spherical. The differential equation, ordinary second order differential R variable that you get, R small r is a solution we are trying to do. So R theta phi, so the differential, second order differential in R became this, okay, which is what is called a spherical Bessel differential equation. It looks like a small change. The Bessel differential equation, for which we solved explicitly using Frobenius method, is of this nature. The first term looks similar, but the second term had, instead of 2, it had x, and the last term was x square minus n square y equal to 0. And we said, supposing it's new, let's say it's not an integer, then the solutions are j nu x and j minus nu x, right? I mean, these are the two solutions we can get, or at least two independent. When it is, if nu is an integer, the other one is a Neumann function. That's what we say. Bessel function of second kind is the Neumann function you get. So I know this. We have already done j nu x. What is Bessel function? We know this. So from here, how do I get the solution of that rather than solving explicitly? How do I get it? Okay, so that's what we are going to do. And the solution is normally called spherical Bessel function of first kind and second kind. We normally denote it by small j rather than big J. Okay, so I will. So this is something we already have. You already know the series form. We already said what is j0x, j half x, j minus x, and all you calculated. If you remember, j half x had a very nice expression, root 2 pi over x, something sine cosine x, or something like that. The other one is root 2 pi over cosine x. So all that we know. So knowing this, okay, I am going to calculate the solution of this. Okay, so that's what we are going to do. So what we do is see how I can transform this to that differential equation. I want to make a transformation, and then we'll try to predict this. What is the, what's R basically. So let's make this transformation. Let the solution be something. I'm going to make this transformation, okay, and say this SR satisfies eventually that Bessel, so that way I know the solution. Okay, so we have to make, this is the transformation I'm going to make, and S will satisfy something like this. Then you will have maybe maybe R square S double prime R S prime, something of this. It will satisfy that. Okay, so then I know what the, since I know what the solution is, then this is nothing but R to the power minus f times Bessel function. Okay, that's what we have to convince ourselves. Okay, so let's. It's going to be a lot of algebra because I did all that. I'm going to quickly do it. So R prime is nothing but negative n minus x minus n minus 1 SR plus R minus half S prime R. Okay, so just the first derivative, right? And R double prime R, take the second derivative, which is nothing but n x minus 1, which is minus half SR plus R minus 3 halves SR. So that is the first term, all right, plus negative nx minus 1. That one is S prime R. I'm just writing it as is, right? Plus R minus half S double prime R. Okay. So let's simplify this. 3/4 of R minus half SR minus half, so those terms I think this should be S prime. Okay, so I want to combine these two terms. Okay, there's a minus sign there, so I can write it as negative R, negative 3 halves S prime R, okay, plus R minus half S double prime R. All I've done is just combine them, so I have R double prime. I'm going to do R square. I'm going to multiply by R square, so I get that term also. So let's see what happens. So R square, R double prime, R will be the first term, right? I mean, so we just have to keep the algebra a little bit straight. R square would be 3/4 of 2. This is what 2.5. So negative half. R minus half SR. Okay, so that is that term. And R square, if I multiply here, I will have negative, let me just write down here in this space, negative R minus half of S prime half. Okay. So this will be R 3 halves of S double prime R. Okay, so I'm trying to get this done. Let's, I shall align them a little better, you can see me better, but anyway. 2r, r prime r, this next term I need, will be minus SR. So multiplying by 2r, right? Now it becomes positive because it's 2r and then s prime r. And the last term is, I also have to have the transformation. So I do have what? K square r square minus l plus 1 r. That becomes k square. R is that, right? So the first term is r 3 halves. R 3 halves SR, and then minus L times L plus 1 R negative half SR. Okay, all I've done is just keeping track of the algebra here. Okay, so when you combine these terms, now let's see what happens to our original differential equation. All right, maybe we should start with the R. This one is okay. So this equation has become R 3 halves S double prime R. Okay, that's the second derivative term, and the first derivative terms are what? I got this. I got that. What else do I have? Only two of them. Okay, plus R halves S prime R. Okay, this is the last term. I got many things. Okay, let's collect the last term, plus k square r to the power of 3 halves. Okay, SR will be there. I'm going to take that. And what else do I have? SR is here, and I have got here. Okay, that's it. And I also have to have that. Okay, I will put that in a minute. But I have other, so this will become 3/4 minus
1/4.
It is 1/4, a negative 1/4.
Negative 1/4.
Okay, so I have a negative 1/4 r to the power minus half, right? So these are all, this has got many things, SR. Okay, this is a term, coefficient multiplying S of R. Okay, so that is one. And what else do I have?
LL plus 1.
I got that term too, right? Negative LL plus 1
RI half.
r to the power negative half, right?
Yeah.
And did I miss anything else?
No.
I got everything?
Yeah.
Okay. Still, it doesn't look like what I want. So now I'm going to multiply, because I want this to be what? X square. I want this equation to be what? X square y double prime. I'm just going to write my x y double prime x square minus n square y equal to 0. This is my Bessel differential equation, right? So in order to get all that is S, right? So this is what we had written. This is a transformation I made. So S has to satisfy the differential equation. S as a function of R has to satisfy the differential equation. So this will be R square S double prime I want. If I want R square, what do you want to do?
First take R half common.
R.
Yeah, or multiply by R to the power half, right? I mean, multiply is easier. multiply by r to the power of half, right? So that will become what? R square s double prime r.
Multiply by means taking common out.
I can also, yeah, you can take it,
Yeah,
it's
it's-
1.5, it's the same thing, right? So multiply, this will become r, right? I mean, yeah. Alright, and then the last term is what we have to, is the crucial one. So what, r square, I multiply r, this has become what? R square, right? So this has become k square r square, and this one has become what? That will cancel, right? So I have negative all these things. So can I write this term as, let me just, okay, sorry, I already have it, go to 0. So r to the power minus half will cancel, right? Because of I'm multiplying by r to the power half. All I have is negative quarter. So this is nothing but what? This term is minus L square minus L minus 1 quarter. That's what this coefficient will become, which is that, right? L square 1 quarter and 12, and negative sign is outside. Now this looks like a Bessel differential equation, right? I mean, so the solution of this was j sub n x. I mean, you can make one further transformation, kr equal to x or something. You can make one more transformation, but you can already guess what is s. What is s of r? If I have to write the solution here, the first Bessel function, first kind, if I want to write, what is it? By analogy, what is the only thing is n square has become L plus half. Okay, so this solution is j sub n x. So what should I write this then as? J of
J of
what is the argument
L
and what
plus
is this?
1 by 2.
L plus half, right? N has become, or new, whatever you want to call it. In this case, it's not integer, so let us say it is like this. And what is the argument?
K is equals to 1.
Kr. Okay, so this is my equation, right? So this is what this has become, my solution S of r. But I'm interested in this. This is the spherical Bessel function. My solution r is then what? This is my solution for r, because that's what my goal is, to get this, find out what r is. So r is nothing but r to the power minus half of j of, this is the first solution, Bessel function of first kind I'm writing. So this is my first solution. Is this clear? I will change the notation in a minute, okay? But because I have right now. So the word spherical I've added. Is it clear? What I did was just made this transformation, converted the Bessel, original spherical Bessel differential equation to something which looks like our Bessel differential equation, for which we got the solution. And from there I said, okay, if this is the case, I make the analogy and say my nu has to be nothing but, this will be in this case j nu x, nu is nothing but L plus half. And my argument there, it was x should be kr. Is this clear? Okay. So this is what we do, and then let me just write down. There's one more stuff we have to do. Let me, how it's written in the books. I need to get it in that form. So the books will represent this part in the small j notation, which is spherical Bessel function. Okay, so they write it in this form: j of if it was x, let us say, it now I'm making from r to x, so that, and I will in a minute explain to you, this r will become x, let us say, in this case, jl plus half, my argument has become kr has become x right now. Now this r is that, okay, but I have put this, I have this, right? I mean, you don't have it. And when we got it, it looks like this, right? This is what it looks like. But I have added a constant, which is, I'll tell you why we also added. I have added this normalization factor. Okay. In a minute, I'm going to tell you why we put that normalization root pi over 2x. Okay, so this is what is called a spherical Bessel function of first kind with all this normalization, root pi over 2. R has become root of x because my argument is x now. Okay, spherical Bessel function of first kind. Now, the reason is they want the lowest Bessel function J0x to have a very nice form. They want it as sine of x over x without any normalization factor. That's why we are multiplying by that. I will. You know what? If you put L equal to 0, what is J0x? Right, this is what it is. And what was j half x? We had proved this in the class, and you had proved as homework j minus half x. What was j half j?
Pi by root 2.
The other way around. Root 2 over pi. It's the other way around. Okay. X
Pi.
and sine of x. This is what you had.
So we need to multiply by this.
Yeah. So we multiply by that, then you get a nice form. That's all it is. That's the rationale for why. I mean, there is. Without why they added this square root of pi over 2 constant, which a constant time solution is going to satisfy differential equation. So that J0x has this nice form because J half is that. So J half is square root of 2 pi over x, and then you will have sine x. And these square root of x are there, so J0x has this nice form, sine x over x. Okay, this is the reason for it. So the second solution of spherical Bessel differential equation, it doesn't have singularity actually. That's a nice one because of the way it is given by the same way, square root of pi over 2x, we write. Okay, I'm going to now write it nice way so that you know why it is there. It's written like this, same normalization you put, and this is your Neumann function, but L plus half x. Okay? Because this equation will have two solutions. One, if it is, you can always have j minus nu, or you can always have y nu x, which is a linear combination that we have. So these are the two solutions of this differential equation. Right? Now, if you remember y nu x, the definition that I had given was, it's a linear combination of the first solution, cosine of nu pi, some weight factor, this is the definition of the Neumann function or Bessel function of second kind, is this. Okay, that is the definition. And so if I have to calculate for the spherical function, it is a combination of j Lx and This eta Lx are the solutions. This is one solution. This is a spherical Bessel function of second kind. Now, what is y of L plus half? If I put L plus half, what is that? Okay. What is that term? The first term?
Sine L. No, sine pi L.
Is it a new cosine of nu has become L plus half, right?
Okay.
Cosine of
Yeah, it's sine of pi L.
cosine A. Let's do it that way maybe. Okay. Cosine A, cosine B. That will not contribute because of that, right? Minus sine A.
No, it's
Sine B, right? So so you do have L pi, and if L is an integer, that will go away. So that is not contributing. Okay, so this term,
goes to 0. First
Yeah.
term goes to 0.
but that one will, this will become, okay, I'll write down this in a minute, is nothing but minus 1, which is L plus half. L is, let's say, an integer for us, okay? L plus 1, J of minus L minus half X. This is what this
Yeah.
y of L plus half becomes, okay? Negative, whether it's in denominator or numerator doesn't matter, right? It is. So y half then is nothing but minus 1 to power times j minus half x, okay? And j minus half x is, we had, what was
Cos x.
is because we just had it a few minutes ago. J y half x then, because I know what that is negative of cosine is it the other way around, right? It's root 2 the other way around. Yeah, it is. I got a negative sign. That is important. Root 2 over pi x times cosine of x. That's what that is, right? So my eta half x, which is my Bessel function of second kind, in that case is simply negative cosine of x over x. Alright? So the eta of 0, sorry, yeah. L equal to 0, right? I mean, this is L equal to 0, so y have y, okay. So knowing the whole thing is, if I know J0 and eta 0, I should be able to calculate all the higher order Bessel functions. So I know the lowest Bessel order functions, spherical, which are very nice form. Eta 0 is, what is J0 was? I've written there, sine x over x. And eta 0 is negative cosine of x over x. Very nice closed form function. And you can calculate the higher order Bessel functions, the spherical Bessel function. There is a very nice form, almost like a Rodriguez formula I have. I'm not going to prove that, but that's also the reason for getting it in this nice closed form, because you can differentiate and get all of them. I'm just going to write down. So the higher order spherical Bessel functions can be obtained by simply a formula like this. The proof is given in the book. It's a fairly nice proof, actually. where this is nothing but sine of x over x. All right. So this is what you will come across most of the time in quantum mechanics, because we always have spherical potentials and stuff like that. It is a spherical Bessel function which you will come across. So the lowest order Bessel function in this case is sine x over cosine x, and the other function is not the second Bessel function second kind is not blowing up, because it's JL plus half is coming, right? So it is only when it is integer it blows up. So the spherical Bessel function does not blow up. Okay. So eta naught is even the importance of the writing the Neumann function originally, right? I mean, it's the in integer cases you have to use L'Hopital rule to make it to work. So you do have very nice form. So you can calculate both solutions in a nice form. I mean, Bessel, if you will have excited states and stuff like that. So yeah, very easy to calculate J1, J2 and everything. All you have to put, you have to differentiate one more time, you get it. And this formula was actually obtained by, the proof is actually, I'm not going to prove it because it is not needed at this point. But I had proved a relationship for you as a part of the generating function and recursion relationship. And that is what helps in getting this particular relationship. If you remember, one of the identities that we got was the following: x to the power minus mu j nu x, right? This was nothing but for the Bessel function. First kind we got that. In the spherical Bessel function, I will use this kind of relationship, and all I know is they're connected, right? The two, the big J and small j's are connected. So you can, from here, you can prove that particular relationship. I mean, it's an iterative way of proving it. I don't want to take the time, but all I want you to at least know this, the lowest order Bessel function, and this is the most important thing, right? I mean, the two are connected through this transformation. You have r to the power minus half times Bessel function of L plus half. Okay, so this is really your JL without normalization is something of this nature, right? This is the connection you have. Okay, so this, which I wrote it as JLX, x to the power minus half, JL plus half x. You have to know this is the connection between spherical Bessel function of first kind and the normal, the one which you got from the cylindrical coordinates is the normal Bessel function. Okay, so this is the only thing you have to, the important thing, they're connected. Okay, I mean, and we studied the property of J half x, which is helping us to calculate this. Okay, so all that, they're all connected. So we're just building on what we had, okay, on the knowledge that we had. All right, we'll stop here today, and hopefully I'll be successful in sending the homeworks to you today. And
that homework we need to submit on Thursday or next?
no, Thursday you cannot do it. I think we need time, especially the derivative method. So if you want to submit,
then
you can.
after fall break.
Yeah.
But basically,
But
basically on 19th, I think.
not 9. We are coming. Oh, 19th. Yeah, you got a lot of time. Yeah. Okay. Yeah. And not 19th. No. We are coming. I'm coming back on. What? 12th is what? 12th is a Thursday. No, Tuesday, right? There's a class on Thursday.
So our
14th is a class. There's a class
That's
on.
12.
Our fall break is from 9 to 10. It's Monday and Tuesday. We should be back.
Oh, I
that week
see.
on Thursday.
And you are not here for Thursday.
I'm not here for Thursday because that's the day my flight is actually. So.
So the 17th
Yeah.
is our next
There's
class.
Yeah,
right.
17th.
17th. Right, because what I knew was there's a class before the exam, but I didn't want just one class before the exam, right? I mean,
So basically 17th.
17th you have to, yeah, correct. Yeah. So the derivative method, don't worry about if you don't get the actual result. I want you to know the methodology